In the second part of this lecture, we'll understand how to use the frame pointer, and we'll first motivate why we need the frame pointer in the first place. Let's consider that I have a function foo that calls a function bar. And the function bar contains this code. So bar has some local variables. The important thing here is that inside a conditional statement, inside an if statement, bar allocates an array of 3 positions. Whenever I allocate local variables or a local array in C, those values are allocated into the stack. So I need to put these values into the stack. So here's my stack. And let's say that I am at the point indicated by the arrow immediately before the call to bar, and that the stack pointer is pointing at this position into memory. So now I do the call to bar. When I do the call to bar, at the beginning of the call to bar, I'll have to create space, and I'll need to create a minimum of 3 spaces here. I need to have space for the return address, because let's assume that bar may call another function. And I also need to have space for x and y, local variables in bar. Now, let's say that I generated the code for the statement pointed by the arrow here. This is an addition of x plus y. The result goes into x. So to do that, I need to load the value of x first. To load the value of x into a temporary, let's say I put in t0, I'll be using the address 4sp, because there is an offset of 4 to the value of sp to get to x. And then I'm going to load y, and to load y, my offset is 0sp. Then I reach the line in the program where I allocating an array of 3 elements inside that conditional. When I do that, I need to increase the size of the stack by 3, so the value of my stack pointer changes. And after that, I need to execute this statement. So now I need to be loading the value of x and y again. But now, when I load the value of x, the offset to the stack pointer is 16, no longer 4, because the stack pointer has changed value due to that allocation of the array A3. Same thing for y. The offset for y has changed, no longer 0, now it's 12. And then when I get to the end of the if, according to the C conventions, that array goes out of scope, therefore it is deallocated from the stack. So at that point, the stack moves back to this position. And when I go to access the x and y, at the bottom here, the last statement that I have in this slide, I'll be having to use the offsets that I had used before. So the main problem that I have here is that in my assembly program, sometimes I have to use the offset 4, sometimes the offset 16 to access x. And if you imagine that instead of a conditional here, you had a loop where this allocation is inside the loop, the situation would be even worse. We would like to have a way to address the variables in my program such that the offset that I use to address all the variables is always the same. The answer is to use something that's called the frame pointer. It's another register in the processor. And when I'm using the frame pointer, the frame pointer always points to the beginning of the frame of a given function. So if the frame pointer is at that position before I call bar, so when I'm here, it means that all the allocation for any variables in foo are between the addresses 4000FF0 and 4000FF8. So there are 3 words that have been allocated into the frame of foo. So now when I do a call to bar, what we're going to do is we're going to change the frame pointer to point to the beginning of the frame of bar, and we'll change the stack pointer to create the space that we need. So now we have the frame pointer pointing to the top of the frame and the stack pointer pointing to the bottom of the frame. When I access the values of x and y in this program now, I will not do the accesses based on the stack pointer, I will do the accesses based on the frame pointer. Therefore, x would be at -4 FP, and y would be at -8 FP. I then allocate the array A into the stack, which will cause me to grow the stack. And when I get to generate the code for that second additional statement that's inside of the conditional, I again will access x with an offset of -4 and access y with an offset of -8. Note that the offset that I use to access x and y is the same as before. There has been no change. And the same will be at the end when I do the next access. So whenever the value of the stack pointer may change during the execution of a procedure, we should be using the frame pointer to have a fixed reference that's at the top of the frame to access all the variables that are allocated in this function. When I finish execution, my stack pointer will return to the value that it was before in the frame point, but now how do we go back to the original frame pointer now? Because if we haven't saved the frame pointer, we don't have it. So the answer is that we're gonna have to save the frame pointer. So the motivation here is that some procedures may change the stack pointer during its execution. If that's the case, the sequence that we should do is first we're gonna have to save the frame pointer so that then we will be able to restore it in the end of the procedure. Then we'll move the frame pointer to the first position of the frame. And then we'll always use the frame pointer to access the stack, and then we're gonna restore the frame pointer. This will be the sequence of steps that we need to do. So here's an example where I have now the colors frame is illustrated as those three words that I have there. And originally, during the color, those are the values of the frame pointer, the stack pointer. Then I do the call. When I do the call, what I'm going to do first is to move the stack pointer by only one position, or one word means that I'm going to be decrementing the stack pointer by 4. That we're going to create a space in the stack for one word. I'm going to use that word to write the value of the stack pointer at that position. Then I can move the frame pointer because I have saved the value of the frame pointer. I have a way to restore that. And then I move the stack pointer again to create the space that I need for the rest of the frame. So in a more concrete example, the instructions that I'm going to be using is I will be decrementing the value of the stack pointer. I'll be moving the frame pointer to that position. And now that I have the frame pointer saved, I'm going to copy the stack pointer into the frame pointer. So this is my new frame pointer. And now I can move my stack pointer down to create the space that I need for the frame of for the colors frame. And I will store all the access that will happen in this code now will be in relation to the frame pointer, never in relation to the stack pointer. Now I got to the end of the procedure and I need to return to the caller. How do I do that? I will restore all the values using, first I restore all the values using the frame pointer. Once I finish restoring all the values using the frame pointer, I will move the frame pointer back to its position by doing this load of using the address that the frame pointer points to now and take the value from that position and put into the frame pointer. So the instruction looks like this. It's a load word fp0fp. So now I have moved the frame pointer to its original position, And now I can move the stack pointer to its original position. And as we illustrated before, the values that were in the frame of the callee do not disappear. They remain in memory, but they are no longer part of the state of my program, and they should no longer be used or accessed. And finally, I return from my procedure. So to recap this part of the lecture, what we have learned here is that when I have a function that may change the value of the stack pointer while executing, I should be using the frame pointer. So by saving the frame pointer first, move the stack, save the frame pointer, and then move the stack again to create the frame for the callee. And then I have to restore the frame pointer at the end of the procedure. We have seen an example of how we do that. We illustrate with the movement of the stack pointer first, and then the frame pointer allocation of the frame, the callee's frame. And this is what we had for this lecture.